Good afternoon, everybody. The intent of this video is to work through one of the problems that we did not get class time to do involving physical pendula, and this is the grandfather clock problem. It reads, a grandfather clock is a pendulum that consists of a thin brass disc of radius 15 centimeters and a mass 1 kilogram that is attached to a long thin rod of negligible mass. The pendulum swings freely about an axis perpendicular to the rod and through the end of the rod opposite the disc, as shown in the figure. If the pendulum is to have a period of 2 seconds for small oscillations at a place where the acceleration of gravity is 9.800 meters per second squared, how long do we need this rod length to be? So as we showed in class and also in the book, the period of any pendulum can be written as 2 pi times the square root of the rotational inertia of that pendulum divided by the mass divided by g and divided by L. But you have to be a little careful in this problem. This L is the distance from the point of rotation to the center of mass of that physical pendulum. And because we're told to ignore the rod is essentially massless for our purposes here. The center of mass of this system is down here in the center of the disk, which means, L here is not L here, and we'll have to be a little careful when we write this. If you have a simple pendulum, again, just a point mass on the end of a light rod or string, the equation simplifies to that, but that's not this case. This is a physical pendulum where the size and mass of that disk matters. All right, so how do we proceed? Well, we're going to need to know what the rotational inertia of this thing is, and the rotational inertia of this system is going to require us to use the parallel axis theorem. So it's going to be the rotational inertia of the disk about its own center plus the rotational inertia of treating this disk as a point mass. What does that mean? Well, disk about its center, we have our table of rotational inertias here, and a disk or cylinder about its own center is 1/2 mr squared. So that's 1/2 the mass of the disk times r squared, plus the rotational inertia of this thing treated like a point mass. And so then we go from the center of mass to the rotational axis. We have a mass of m there, but the distance that it is away would be L plus r squared. All right, so now we can write, and I'm just going to keep everything symbolic now to see what we need to do. T is 2 pi, and our rotational inertia is 1/2 mr squared plus m L plus r squared. Now in the denominator, we're going to have an m, we're going to have a g, and then again, this distance is the torque distance in effect. So it's the distance from the rotational axis down to the center of mass of our disk here. So this is also L plus r. And now we see that it's going to be fun, because a lot of times in these, if you just have L in the numerator, well then you're just doing algebra to solve for L here. But given that we have L in the numerator and the denominator, I sense that a quadratic equation is in our future. So let's go ahead and get there. T over 2 pi, and I'm going to go ahead and square that, and then this stuff is taken out of that square root. In addition, these masses are all going to cancel, right? So I can write this as 1/2 r squared plus, let's see, L plus r squared. That's L squared plus 2LR plus r squared, if we expand that, over g times L plus r. All right, I'm going to get rid of my denominator. So g times L plus r times t over 2 pi squared equals 1/2 r squared plus L squared plus 2r, I'm going to move L to the end since it's the variable we don't know, plus r squared. Boy, this just doesn't look fun. All right, and then I'm going to put everything on the same side of the equation in doing this. So if we start with L squared, we only have the L squared term here. All right, so we took care of that. Now, in terms of terms that have L in them, I've got this one, so 2r. Then I got all of this leading term, right? So I've got a minus if I move this over here. G t over 2 pi squared, yep, times L. More and more fun. And then, let's see, 1/2 r squared plus r squared is going to leave me with a 3/2 r squared. But again, I got this, let's see, gr t over 2 pi squared. So this is minus g r t over 2 pi squared equals 0. All right, now I notice, sorry, I've been writing half of that off the video, but here's all our terms. I just basically moved all of this stuff over to this side. All right, well, now we have it set up. Now it's a matter of figuring out what each of these terms are. This is nice. The leading coefficient on L squared is just 1, but I need to calculate what 2r minus g times the period over 2 pi squared is. So 2 times a radius of 0.15 minus, and then 9.8 times 2 over 2 pi is the same thing as 1 over pi. That piece got squared. Oh, this is actually a negative 0.6929476. I'm going to keep all that because it's asking us for a fairly precise answer. Now I need all of this stuff, which is the stuff that doesn't have L in it. So 3/2 r squared is 0.03375. gr t squared over 2 pi squared, so 9.8 times 0.15 times, now 2 over 2 pi again is the same as 1 over pi. That's all squared. Minus 0.14894214. Okay, so if that's, whoa. That's collectively negative 0.11519214. Probably don't need necessarily all those digits, but now I've arranged it into the standard form for a quadratic equation, and I am going to go and use a quadratic equation solver to do that, because while I do remember the quadratic formula, it is more efficient to do this otherwise. So 1 is my leading coefficient, then negative 0.6929476, and then my third one is negative 0.11519214. And I have two roots. One of them is negative, so that doesn't make any physical sense in this situation, but the other is positive, and it is, let's see, 0.831, and we want to the nearest tenth of a millimeter, so I believe that's that, right? Because there's your millimeter, and that's your tenth of a millimeter. 0.8314 meters. All right, so while there is in this problem some mathematical detail at the end, the main focus should not be on that. You know, quadratic equations crop up every once in a while and you just have to fight through them. But big picture, you're using this expression for any pendulum when you're solving a physical pendulum problem. And much of the work involves writing an appropriate rotational inertia for that. It was just kind of unfortunate that when we got to this stage, we had to go to the quadratic equation to get to the answer. But there it is.